Well, hello friends. Welcome back to the program. Today we are going to look at JavaScript performance. And specifically, I would like to make JavaScript heap allocation faster. So I was profiling the JavaScript test runner that we have. So we have this program called test.js, and it runs our entire JavaScript regression test suite. So you can see here it currently has 1,276 tests that pass and one that we skip. So about 1,300 tests, and it runs in about 1 second cold and then about 800 milliseconds hot or warm, what do you want to call it. So the thing that differs between the first run and subsequent runs is just the disk cache. So all the tests are now in the disk cache. And if we grab a profile of this, I'm primarily interested in the warm time, by the way. So let's profile a run of this, and then let's take a look at the profile. So if we look here, and let's use top functions actually, then we can see that heap allocate cell is 26%, which means that 26% of runtime is spent allocating heap cells. And out of those 26%, 8% is garbage collection, because sometimes when we allocate and we don't have any cells, then we try to garbage collect and see if that frees up any cells. But as you can see here, when we do have a cell, or when we do allocate, the thing that ends up taking time is creating new heap blocks. So heap block is, it's a 16 kilobyte block that we subdivide into what we call cells. And every JavaScript object occupies one cell, and then there are different sizes of cells, but they all live in heap blocks. And the bulk of the cost of heap block allocation is in mmap, which calls to the kernel. And yeah, like mmap is just expensive. So I think what I would like to do is implement a recycling optimization where we recycle heap blocks. So at the moment, when a heap block is freed by garbage collection, we just unmap it. But if we would keep some heap blocks around, we could recycle them in subsequent allocations and avoid having to mmap again. I think that would be a very sensible optimization, and it's one that we already do in libcmalloc. So the libcmalloc already does block recycling. So I guess the idea now is to teach the JavaScript garbage collector allocator to do the same thing. So let's look at the heap block class. So we can see here, heap block is in the JS namespace, has a block size constant that's 16 kilobytes. So we always allocate 16 kilobytes for these blocks for a couple of reasons that are not important to what we're doing right now, but we always allocate 16 kilobytes. And this is the function that does the job. So heap block create with cell size, and then you provide the heap and the cell size. And the Serenity block here is grayed out in CLion, which is a bit annoying, but I don't know exactly how to fix that. But yeah, so what we do is we create a name for the heap block, which we then pass to mmap, so that the reason that we do this is so that if you run libjs, so here I'm running the JS REPL. Let me create an object, and these heap blocks in the address space then have names, so you can recognize them. It's like libjs heap block 128 tells us that this region is a 16 kilobyte libjs heap block with a cell size of 128. So it's just a nice way to be able to identify them in memory map listings. So we create a string like that for the name, and then we call the operating system's allocator to allocate the block. But what if instead we had a pool of blocks, say? And maybe we would put that on the heap. So let's see. We would put that in libjs, heap. Maybe we would call it a block allocator, something like that. And then what do we put in the block allocator? I'm not exactly sure. We'll figure this out though, don't worry. So what goes in here? Namespace JS class block allocator. And I guess, I think we're gonna have a block allocator for heap. So we will tie it to the heap, and then we'll let this other guy, the guy who's allocating blocks. So let's say that we always want to create the name, but then we'll do something like block is heap block allocator allocate block, right? And then we'll let that guy do this stuff. So it will just return a 16 kilobyte block. Should we pass in a cell size actually? Maybe that would make sense. Cell size. Let's try that. And then he can take care of, wait. This factoring gets awkward. I think maybe we'll let the block allocator simply return a void star for now, and then we don't worry about constructing that. So we will just allocate yeah, so really this will be more like a generic block allocator, not necessarily for heap block, but it can allocate anything. It will recycle earlier blocks. Yeah, okay, it'll make sense when we get it together, I think. So step one is make sure we can see the heap. And then let's give it a block allocator. So I think let's just put that here, block allocator. So these, oh, here we have allocators. Wait, what did they do? They have cells. Right, so these are cell allocators. Maybe they should be renamed to cell allocators, actually. But let's not overthink it. At the moment, we are only working on block allocator. Yeah, and then we will also add an API to access the block allocator. We can just put that here. And block allocator. Okay. Cool. And he needs the back pointer to me. That's fine. Okay, block allocator. Explicit. And I guess, so what we want here, let's make it simple. Let's just have a simple vector of blocks, right? And act vector and libjs forward. The API would be something like allocate block size to size, and also deallocate block. Yeah, let's do something like this. I think that's a decent API. Do we actually need the heap for anything? I don't know what I thought I was gonna do with the heap. Maybe we don't need the heap. Okay. Okay. And then maybe I'm making this overly generic. Like, I don't want to support multiple block sizes. So maybe what I really want is something more like this. But I can't see heap block here. Okay. Let's not overthink this. Let's just simplify. So it will always use the heap allocator block size, or the heap block size, instead of allowing you to specify. That'll be nicer. And then we get rid of that thing as well. Okay. Yeah, I got a little carried away overthinking how generic this needs to be, and it doesn't need to be generic. So if blocks is empty, then we will just create a new block. So return whatever that code was doing here. We want to do this stuff. So like that, essentially. So I guess we need sys and man for that. Return block. Otherwise, we will. Maybe it's easier to write this the other way around. If it's non-empty, then return m blocks take last. Yeah, that's easier. Okay, and then when you deallocate a block, then okay, I should probably add this to the CMake file because syntax highlighting is not working right. So where is the heap? Here. Klook. Where's the thing here? There we go. That's fine. Where is aligned alloc? This is the Linux code path, I guess. It's in stdlib. Okay, well, we can get stdlib. Don't mind if I do. And then when you deallocate, let's verify that you're not deallocating a null pointer. And if you deallocate, we will just append it to the list of blocks. And I guess, well, this thing should probably have a limit, right? So let's say that we limit it at I don't know, 16K per block. So 16 times, how about 1024 blocks? That's a bit many. That's 16 megs. 256 blocks, that would be 4 megs. I don't know how many we should have. Say 128, that feels fair, like 2 megabytes of cache. And then we can come up with strategies to like empty this cache if it, the block allocator cache, if it turns out to not be useful. But I think as long as you're allocating and reallocating, I think this will be helpful. So let's see if, let's just do something like this at first. So if, then just delete block, I guess, or map the block rather. Heap block size. Verify not reached. Because the map should definitely succeed. Okay. And otherwise we will just keep it. So if we map that succeeds, we will return here. Otherwise we keep it around. So let's see if we can make this work. Allocate block, sure. Block, I guess we gotta do something like that. Yeah, this API is a tiny bit awkward, but let's tolerate it for now. Also the name, right now we're not passing the name anywhere, so we gotta figure out how to plumb that into the thing. Let's just see if this works. Oh, we can just pass in a name here actually. So allocate block. So we'll do something like name. Yeah. May be unused because it's not used on Linux. So if you're not familiar with libjs, we actually build libjs both for the host system and for Serenity. So that's why we have this ifdef. And we can actually run libjs on my Linux machine for testing, and we do that quite a bit. It's really useful. We've been doing a lot of testing that way, although recently we started running tests on Serenity as part of our continuous integration testing as well. That's been really cool. So now when you make a pull request to Serenity, we will actually run, as part of CI, we'll like spin up an instance of Serenity and run tests in it, which is really sweet. So it would be a bit disappointing if this doesn't help, but it seems to me that it's, I mean, it's fairly straightforward. The fact that we're seeing so much mmap time spent below block allocation, and the recent changes done to libcmalloc, where we now recycle blocks, were immensely helpful. So I am somewhat confident that this will help. Test.js. Not really making a difference here, at least, that I can tell, but did I do this right? I wonder. If blocks is non-empty. I'm probably never deallocating the block, right? Yeah, that's what I'm doing wrong. I forgot about deallocate block. So the operator delete on heap block is gonna have to do Oh wait, he doesn't know where the heap is. Oh, that's kind of irritating. Right. Wait, who deletes these? Delete block. This thing does. The cell allocator deletes the heap block when it becomes empty. Okay, it's a little bit of spaghetti warning here, but all right. So instead of doing that, we can do, well, we still want to run the destructor, but then we want to actually put the allocation back. So really what we want to do is like that, and then this is kind of gnarly, but it is what it is. Can we get to the heap from here? Allocator doesn't have a path back to the heap. Well, this guy has a path to the heap though. Block.heap. Haha. So we'll do this. Heap dot block allocator. Deallocate block. Okay, so now it should go back in the pool. And hopefully we should be able to reuse it. Okay, yeah, look at that. Down from 1 second to the 8s, and down from 800 to 539. That is really nice. So, and like, it's good that we're actually running the test suite as our benchmark, because then we would learn right away if the tests stopped passing. So let's look at that profile. Okay, so we got the heap allocate cell all the way down here at 9.5%, down from, what was it, 26%? So that's a fantastic improvement, actually. Now garbage collection dominates the time spent in cell allocation, and heap block allocation is a measly 0.57%. So just by implementing basic block recycling with a 2 megabyte block cache, we were able to effectively get rid of all the time spent in block allocation. So really, really good. And just a rough estimate, what did we have before? It was like 840, say, and now we're at, say, 550, 540, 540. So what, 550? Is that a 35% improvement? Something like that. I guess it depends on how you cut it. Yeah, something like 35, 34%. That's really kick-ass. Very, very cool. Now, of course, the downside here is that we now eat a 2 megabyte cost per JavaScript heap. But I feel like that's not terribly much in the great scheme of things, although let's still investigate what happens if we only do 64 blocks, which would be, I guess, a 1 megabyte block cache. Oh, okay, so it's like roughly the same. Wait, what if we go even lower? Maybe we can go even lower. Like, the less memory we have to spend on this, the better. Okay, now it's starting to go up a bit, but it seems like 64 was pretty decent. So caching 64 blocks, to me, that's definitely worth it, right? It's 1 megabyte of memory for a 35% speed improvement. Like, I don't think that seems completely justified to me. So let's roll with it. So let's see, max cached blocks. And we can put that down here. So const expr max max cached blocks is 64. Seems fine. And then we also need to make sure that these get deallocated on destruction. Otherwise, that would be a bit sad if you instantiate multiple JavaScript VMs that we don't do that. So let's say that while mblocks is non-empty, I gotta remember to use the .not thing. There we go. Deallocate block. Wait, this logic is not gonna work. I just want to m on map, actually. So I want to m on map everybody. Yeah, that's what I want to do. If that fails, I think I still want to learn that failed, and we'll say verify not reached, because if we had a pointer to a block that fails to m on map, then something is wrong with our state, and I think we should not continue executing at that point. I've had some discussions with people recently about like the value of stopping a program right away if there's some inconsistency in the state, or if something does not make sense in the state. And I'm a huge fan of just killing the program whenever the state is screwed up. But there are those who feel that it's better to try to limp along and recover with whatever grace is possible. So it's interesting that there are like these different schools of thought on that, but they have yet to convince me of their case. Okay. So this feels very reasonable. I guess let's also verify that it still runs on Linux. It does. It's a bit slow, but probably that's because I'm compiling at the same time. Let's see when it finishes up here. Come on now. Yeah, okay, look at that. 530, 530. This is really cool, actually. We are now within spitting distance of the Linux runtime of the test suite. Historically, Linux has always been much faster at running our test suite. And look at frickin' that. Identical runtimes. That's so cool. I don't think I've ever seen that before with test.js. That's really exciting. See, we're even faster sometimes. That's so awesome. I'm really happy about that. And I mean, of course, what we're doing now is we're sort of bypassing the kernel and staying in user space for more of the time. So what this really tells us is that our kernel is slower at mmap than Linux is. And we knew that, but it's still cool that we can do an optimization in libjs, and with that optimization in place, the difference in cost of mmap between Serenity and Linux is essentially no longer relevant to the performance of our test suite. So cool, very, very cool. Cool. Okay, let's make a commit out of this. So let's see. Block allocator. Just adding the file, blah, blah, blah. This stuff here is slightly awkward. We can definitely find better ways to factor that. I'm just going to kind of ignore it at this moment. Also, what's up with that? I didn't mean to do that. Maybe we should add a little comment. So let's see. Heap blocks are managed by the block allocator, so don't want to delete the block here. Yeah. We don't want to delete the block. We just want to give it back to the block allocator. It's tempting to call it a block pool, but So yeah, that's fine. Okay. lib.js. Recycle heap blocks. Recycle up to 64 heap blocks. To improve performance. This patch adds a block allocator to the GC heap, where we now cache 64 heap blocks up to 64 heap blocks that get recycled whenever a heap block sized mmaps, let's say. Get recycled when allocating heap blocks. This improves this improves test.js performance, test.js runtime by 35%, which is cool. Let's say pretty cool. Yeah. The factoring is a little bit awkward, but I think we can probably tolerate it for now. So let's, yeah, let's tolerate that for now. And I did mention that I wanted to rename allocator to cell allocator. I think that might be a better name because now we have block allocator and allocator, and that doesn't seem, or wait, what's going on here? Allocator has block lists. Do I want to call it a cell allocator? I guess I do. Yeah, I'm gonna call it a cell allocator. Let's slap an explicit there while we're at it. Oops. Oopsie doopsie. And assuming that everything builds, let's just monitor that while writing a commit message. So libjs rename allocator cell allocator. Now that we have a block allocator as well, it seems appropriate to name the allocator that allocates cells something more specific as well. Or not as well. I already said as well. Something more specific to match, let's say. To match it. To match. Yeah. That's good. I think it's good to disambiguate things. So let's do that. No, I wanted that thing. So the first run is a bit slower. I bet we can improve that if we spend some time investigating the disk cache stuff. But let's care about warm runs for now. So here's a little thing I did yesterday, by the way. Notice the little knurling on the splitter there. Previously, it was like you couldn't tell which parts of a UI were resizable. So now I've added this knurling to splitters. Same thing here. I think it turned out pretty good. It gives you a nice little visual clue about which things are indeed resizable. Anyways, little sidetrack. Wait. Yeah, so now it's like other stuff totally dominates. Deallocating heap block is still pretty hefty, but none of that is actually giving the block back to the block allocator. This is all just running destructors, which is much harder to avoid. There are techniques to avoid that, but I'd like to... I don't know. I like to get these more simple optimizations done first. Like the thing that we've done here today is obviously pretty basic, right? But very impactful. So great thing to do. It is weird. We're spending 8% in free, 4% in memset. Ooh, that's chunky. Oh wait, look at that. Almost 8% in memset. Ugh. I bet that somebody could write a better memset and we could get like real gains just from that, because the memset we have and libc is it's this thing right here. So let me show you. It's like this ugly just assembly like repstasbo. And I bet you that we could use some fancy tricks to make this thing go faster. But I haven't looked at it, and maybe somebody will at some point do that, because that's probably money on the table there. Probably the same thing for memcopy and memmove, maybe stirlen, I don't know. All of those like basic things, there's probably assembly language optimizations. Yeah. Anyways, I think I'm gonna be satisfied here for today, because 35% improvement on the whole JS test suite is pretty damn good. So that'll be the end of today's video. So if you made it this far, then I thank you for watching and for hanging out. I hope that you saw something interesting, and I'm obviously very happy with the results. I think the thing that excites me the most is that now we are on par with Linux runtime of test.js. So Serenity and Linux are head to head on test.js performance. Very cool. So thank you for hanging out, and I will see you next time. Bye.